Alright, in previous slide, okay, you have been introduced to Q equals to MC delta T. Alright, meaning we can find ataupun we can calculate the amount of energy required, okay, due to certain difference of temperature. Alright, so as the temperature of an object increases or decreases, we can find the amount of energy, okay, related to the difference. Right. Now, at the same time, okay, the temperature is also related to the internal energy of the system, right? So meaning, these two mc delta t, right? They are equal, right? Meaning the amount of energy, okay, to increase the temperature of the object, okay, is also used to increase the internal energy of the system. Alright, so we have these two can be equate, right? Now let's go through one example how to apply this. A cowboy fires a silver bullet with a muzzle speed of 200 meters per second into the pine wall of a saloon. Assume all the internal energy generated by the impact remains with the bullet. What is the temperature change of the bullet? Alright, so the bullet, okay, is uh, traveling with initial speed of 200 meter per second. All right. So this is 2 VI. Okay, VI equals to 200 meter per second. And then into the pine wall of a saloon. All right. So after impact, okay, the final speed equals to 0. Right. So here we are going to apply the conservation of energy. If you still remember, alright, the conservation of energy states that the total energy is always constant, isn't it? Alright. Okay, so we have that Ki, okay, plus the internal energy equals to K final, okay, plus E final. Right, and then we have Kf minus Ki, so we have delta K. Alright, delta K plus dengan Ef minus Ei, okay, plus delta E equals to 0. Alright, so that's why we have this equation. Alright, now delta K is K final minus K initial, isn't it? K final minus K initial. Alright, and then delta E adalah equals to MC delta T. Alright, the substitute here, MC delta T equals to 0. Alright, so we rearrange the equation since we want to find the temperature change. Alright, so make it delta T as a title here. So delta T equals to half mv squared over mc. Alright, so m can be cancelled. That's why we don't need to know the mass of the bullet. Alright, so we have v squared over 2c. Alright, so the specific heat, okay, of silver, alright, when you refer to the table of list of specific heat capacity of materials, alright, the C silver equals to 234, okay, joule per kilogram per Celsius. Alright, so end up you have the temperature change is 85.5 degree Celsius. Alright, next example. A 0.05 kilogram ingot of metal is heated to 200 degrees Celsius and then dropped into a calorimeter containing 0.4 kilogram of water initially at 20 degrees Celsius. Now, in this question, okay, if you want to plot graph, okay, you may also plot graph like this. Okay, katalah ni T, temperature, alright, and then here we have Q. Okay, ini the energy added, right? Now, the ingot is initially at 200 degrees Celsius, alright, 200 degrees Celsius. So once we put it in a water, initially at 20 degrees Celsius, okay, what happens is that the metal will release energy, alright, okay, we release energy and transfer heat to water. So therefore, bila dia release heat, its temperature will decrease. Okay, will decrease until when you see at the second sentence here, the final equilibrium temperature of the mixed system is 22.4. Alright, so dia sampai dekat equilibrium temperature that is 22.4. Okay, ini untuk the metal. Alright. As for the water, alright, so the water is initially at 20 degrees Celsius. 20 degrees Celsius, right? So the water will gain heat. Okay, it will absorb heat from the metal. Alright, so dia akan increase the temperature until it reach 22.4 degree Celsius. Alright. Okay. Now, you can also make a table. Okay, make a table since we have two substances here. Alright. So here we have the metal. Okay, the metal with mass 0.05 kilogram. Okay, and then we have the water. Alright. The water is 0.4 kilogram. Okay, 0.4 kilogram ni dalam kg. Alright. Okay, then we have the specific heat. Okay, specific heat. As for the metal, we don't know the specific of the metal. For the water, we know the specific heat is 4186 joule per kilogram per Celsius. Right, joule per kilogram per Celsius. Right, and then delta T. Okay, to find delta T, alright, delta T is always T final minus T initial, isn't it? Alright. Jadi T final, okay, same for both. 22.4, okay, 22.4. Alright. How about T initial? As for the metal, it is 200 degrees Celsius. And for the water, it is 20 degrees Celsius. Alright. So from here, then only you can find delta T, isn't it? Alright. So you find delta T for each. Alright. As for the metal, okay, for the metal, the delta T is 22.4 minus 200. Okay, we get negative 177.6. As for the water, we get 2.4, isn't it? Alright. Okay, 2.4 degree Celsius. Right. So once we have listed all this, okay, then we can put it in the principle of conservation, okay, where we have as I mentioned before, delta, the sum of the energy between two substances equals to 0. So here we have only the metal, okay, plus water, isn't it? Okay, plus water, okay. Right, so the water contains in a calorimeter. So we assume that there is no heat transfer between the calorimeter and its surrounding. Alright. Jadi Q metal, we have M metal, okay, C metal, and then delta T metal. Plus Km water, C water, delta T water equals to 0. Alright. So you just substitute all the values here. Alright, M water we know 0.05, okay, C M metal 0.05, and then the one that we are going to find here is the specific heat of the metal. Alright, delta T metal is negative 177.6, okay, mass of the water 0.4, alright, capacity specific heat of water is 4186, and delta T into water is 2.4. Alright, so once you substitute all the values there, so we get the specific heat of metal is 453 joule per kilogram per Celsius. Alright.